Qing Liu actually got his bachelor master's degree from Xiamen University in China in 1983. He came here in 1986 to study for his Ph.D. and graduated in 1989. He has gone to a lot of places, including working at Schlumberger, winning the Presidential Scholar, like Presidential Early Career Award for Scientists and Engineers, plus many other awards. He even went to the White House to get his award, and now I guess he is working both in Duke University and China. I'll let you read the detail of this biography that he has, and let him get started with what he has to tell us on nanophotonics. Okay, please, Qing.
Thank you, Professor Chu. It's an honor to be here for this occasion. So congratulations to Professor Chu and Chu Qing. My talk is on spectral element method for linear and nonlinear phenomena in nanophotonics, because I know that this class is on optics. So, and also I would like to take this occasion to remember Professor Song-Yan Chuang, because he taught this course to me over 27 years ago, I guess. So I will give a few different topics here. I will talk about the challenges in computational nanophotonics, and then talk about the spectral element method we have been working on for last probably 10 years. And then talk about some application of this method in nanophotonics for both linear and nonlinear nanophotonics problems before summarizing. Nanophotonics, the computational for nanophotonics is very challenging in that the device scale could be much larger than the wavelengths. Okay, so typically for the optical frequency range, we are talking about wavelengths of 500 nanometers, around that order. But the computational size can be orders of magnitude larger than that. So therefore, it's very, very computational intensive. So that the size is the one challenge. The other challenge could be the nonlinearity often appear in nanophotonics. So when you want to apply nonlinear optics or laser, you need to model nonlinearity. So here is an example of a large nanophotonic example with finite photonic crystal structure, and you need to model this very accurately. Traditional method of solving nanophotonics problems is finite element method and finite difference method. Finite element method and finite difference method, the conventional way is to use the lower order basis functions. So therefore, the convergence rate is very slow. It means that if you decrease the grid size, the computational cost is the error is going to be proportional to the grid size square. Okay, so therefore the convergence is slow. Therefore, you need a very large sampling density in space. For example, 20 points per wavelength in order to reach an error of 1%. Okay. So therefore, for very large computational problem, if the dimension of the problem is L, and the wavelength is lambda, the sampling density is S, meaning it's how many points per wavelength you have. Then for the d-dimensional problem, the number of unknowns or the degree of freedom is proportional to this L divided by lambda S raised to the dth power. Okay, so therefore, for high-dimensional problem, for example, 3-dimensional problem, it's very costly to solve this kind of problem. If this, if the sampling density is very high. Okay, so we have been working on high-order method, and this method is called the spectral element method. The purpose of this method is to reduce the sampling density. So therefore, decrease the computational cost. Spectral element method, unlike finite element method or finite difference method, it only requires very low sampling density. For example, around 4 points per wavelength in the sampling density. So therefore, we can reduce the computational cost a lot. And we have applied this to Schrodinger equations in the quantum mechanics and in the self-consistent Schrodinger-Poisson system. And in electromagnetic, we start this with a spectral element, a pseudo-spectral element in '97. But other related areas, for example, acoustic, computational acoustic, and elasticity, people have been using spectral element method also. So this method use a tensor product of one-dimensional basis function, and here I give a one-dimensional nth order spectral element. And usually you put this element within a reference domain from -1 to 1, and the grid points are non-uniform distributed, and the basis functions are polynomial basis functions, and here we call this a Gauss, the beta legenda polynomials. They are distributed non-uniformly and to reduce the so-called Runge phenomena. So these are some typical basis functions, for example, for order 6. And for two-dimensional and three-dimensional problem, if the problem is scalar, for example, for quantum mechanics problems, you just basically do the one-dimensional basis function tensor product, and then you can get multi-dimensional basis functions. Okay. Now that's in the reference domain. In the physical domain, often we need to deal with complicated geometries, so you need to have a curve element. And a curve element can be mapped into a reference element by using coordinate transformation. And so then you just need to work with the basis function in the reference domain. Okay. So here I want to compare that high-order finite element method with the spectral element method. And for example, for the fourth order finite element method, this is the typical nodal point distribution. And for the spectral element method, the difference is that near the boundary we have tensor distribution of the nodal points. And the purpose of this tensor distribution is to get rid of so-called Runge phenomena. If you have uniform distribution, then the area actually would eventually grow with the order. Okay, so here we use tensor distribution near the boundaries to remove this so-called Runge phenomenon. Okay. So with this kind of spectral element method, actually you can reduce the computational cost a lot. For example, if you are dealing with a cubic cavity of one wavelength in size in each dimension, then in the finite element method you need about at least 6,000 degrees of freedom. But in the spectral element method, we just need one element with fifth order, and it will be more accurate than this spectral finite element method. And the number of unknowns is only 750. So therefore, you save about 90% of the number of degrees of freedoms in the finite element method. And so another advantage of this spectral element method is that the mass matrix in this method is diagonal because of the orthogonality of the basis function. So therefore, when you solve eigenvalue problems, instead of solving a generalized eigenvalue problem in the finite element method, here we have a regular eigenvalue problem, normal eigenvalue problem, and it's much cheaper to solve this regular eigenvalue problem than solving a generalized eigenvalue problem. So in summary, the advantage of the spectral element method is that it has spectral convergence. So you require very low sampling density, and there's no Runge phenomenon, and also that the mass matrix is diagonal. And this also has a very big advantage in the time domain solution when you use explicit method. Okay. So here I'm going to just give some overview of the applications of this method in nanophotonics. So first of all, I talk about a scalar basis function, but for electromagnetic problem, of course, we need vector basis functions. So here is the vector basis functions for n equal to 2 and n equal to 1, and this is in the reference domain, and we call this spectral Nedlec element. And of course, you need to transform from the reference domain to the physical domain using the covariant transformation. And then you use that basis function to solve Maxwell's equation either in time domain or in frequency domain. Okay, so here I'm going to give a few examples. First, I will talk about nanophotonics, photonic crystal applications. So photonic crystals, of course, are periodic structures of crystal structures. And so traditional method of solving this is using finite difference time domain or finite element method. And the third one is very well-known method is called a plane wave expansion. It's pioneered by Stephen Johnson in MIT. And in fact, he has a very well-known package called MPB. And we are going to compare that, our method with that MIT's solution. Okay, so here is the two-dimensional anisotropic photonic crystal that we worked on. So here we show that the error of our results for TM and TE mode versus the order of basis function, and you can see that in this semi-log plot, you can see that our error will decrease exponentially with the order of the basis function. Okay, and and in fact, you can achieve much more accurate results than the MPB, the MIT package. With only 4 points per wavelength sampling, we can reach error smaller than 0.1%. And for this two-dimensional example, actually, we show that it's 19 times faster than the MIT package with a photonic bandgap structure with more than 30,000 points in the bandgap structure. We have also applied this to three-dimensional anisotropic photonic crystal, and this is one example with an air hole in the photonic crystal structure, and that's the periodic structure with that unit cell. And we also compare with this plane wave expansion method, and you can see that here in the middle we have this plot the bandgap for very large, very high order modes. And plane wave solution, of course, cannot go very far because it's not very accurate for very high order modes. But we can get very accurate result even for very high order modes. And for this case, we compare the speed. It's about 18 times faster than the MPB package with only. And this is again the convergence curve. We have also done this for two-dimensional periodic structures. For example, in the thin film, we drill a lot of periodic air holes in this metallic thin film, and we can see that so-called extraordinary transmission of optical waves through the thin film because of this surface plasmon effect. Okay, and here is the comparison between our result, SEM result. For two different polarization, the holes are not circular holes, they are elliptical holes. So two different polarization will have slightly different transmission coefficient. And you compare this with the experimental result published by Lin in 2006, and you can see very good agreement between them. So the next one I will show is for the nonlinear nanophotonic applications. So a lot of time we want to solve nonlinear problems. One of the application of the nonlinear optics is the so-called second order harmonic generation. Okay, if the material is nonlinear, if you pump in a fundamental mode, fundamental wavelengths, it's going to generate a second harmonic. Okay, and however, this kind of second harmonic generation is usually very weak. So how to enhance this second harmonic is a very important topic here. So here we are trying to use the photonic crystal structure to enhance this second harmonic generation. Okay. So however, to solve this, we need to solve nonlinear equations. So you need to solve Maxwell's equation with nonlinearity. Okay. So we use an iterative solver to couple the fundamental frequency and the second harmonic frequency to solve the problem. Okay. So this is the equation. So you solve the fundamental equation with the polarization due to the second harmonic generation, and you couple with the second harmonic field, and you do iterative solution of these two systems until you reach the convergence. Okay, so here I'm going to give an example on a thin film. Okay, this thin film is made of gallium phosphide thin film. And if you just use the uniform thin film, the second harmonic generation is very weak. Okay, so we want to enhance this by using the photonic crystal. Okay, so we just drill air holes on this thin film, and we want to see how this air holes will affect the second harmonic generation. Okay, so here I showed the comparison between the thin film and the thin film with periodic holes. Okay. So if you have a light coming in, you can have reflection and transmission for the second harmonic generation. So one is called forward, the other one is called backward second harmonic generation. So here I show the comparison here. If you see the dashed lines, one is for the forward, the other one is for backward second harmonic generation rate for the uniform same film. Okay, for the result with this periodic photonic crystal, you can see a lot of peaks there, and those are due to the constructive interference of the periodic structure. Okay, so in fact, at the resonant frequency here, at some resonant frequency here, if you look at this one, we can enhance the second harmonic generation rate by 4 orders of magnitude. Okay, and later on, actually, we have continued improve this to about 6 orders of magnitude by using Bragg refractor in a vertical direction as well. Okay, so you can see the power of this photonic crystal in the design of second harmonic generation. Okay, so so this is a quick talk. I gave you a talk about the spectral element method. The SEM has a very high convergence rate, so therefore it requires very small sampling density. Usually only about 4 points per wavelength sampling will be enough to give you higher accuracy than finite element with 20 points per wavelength. And so, in fact, this spectral element method can also be hybridized with finite element method for multi-scale problems. For example, you can use, for the coarse structure, you can solve this using spectral element. For the fine structures, you can use the lower order finite element method, and you can combine this. In fact, we have developed a solver to do multi-scale problem in a time domain, and this is published earlier. And I have shown some nanophotonic applications, both in the linear and nonlinear regime, to show that efficiency of this spectral element method. Okay, so our ongoing research is doing multi-scale, multi-physics coupling. For example, we are doing coupling of this electromagnetic wave with fluid flow to solve oil field problem. Okay, so thank you for your attention.
A couple of questions. First of all, you talked about high convergence and accuracy. So, what is the accuracy of your models themselves? How accurate?
Oh, the model.
So, in comparison with.
You mean a geometrical model?
No, I'm not done. Second thing is that you compare you say that it's much faster, it's better than FEM, but none of the results or comparisons you made, they were all with SEM and MTB, but not with the FEM. Why is that?
Oh, so actually, so we have also compared with finite element method. Those are published. Those here, because of limited time, I only compare with the plane wave expansion. But actually, this year we also published a paper, and we compare extensively with COMSOL. Okay, COMSOL is using finite element method for both first order and second order basis function. And you can see, for large problem, you can see orders of magnitude difference in terms of computational time. In terms of the accuracy of the model, I guess you are talking about geometrical model, right? So geometrical model for coarse structures, you do need to use very high order representation of the curvature of the geometry, and we do have that in the code. Yeah.
You need to use a PowerPoint to say anything.
No.
No.
Okay. Yeah.
Are there any other questions?
Yes, please. Yes. Yeah. Yes. For large wavelength. Oh, so you mean if it's for large wavelength, then you don't need very high order basis function. So basically, low order in that case will be, in that case we call it electrically small problems. And in that case, you just need a low order finite element will be just fine. Okay.
Because if you do the speed dipole approximation,
yes,
it's much more time to run a large wavelength than low wavelength.
Oh, so I believe that is related to the low frequency breakdown problem. For large wavelength problem, and Professor Chu has worked extensively on that topic. I mean, I believe it's related to the low frequency breakdown problem. But here we are not solving the integral equation problem. That is for integral equation. Yeah.
Okay. If there are no questions, let's give Qing Ho Liu another hand, and let's move on to.